So this is problem 3 from the Jones final exam, and we're going to just start off with part A that says find the planes of a particular zone that are perpendicular to one another. So you can do this in the old video, but right here the two planes end up being 0, 1, 0 and bar 1, 0, 2. And you could pick other planes. Maybe there are other planes that are perpendicular to each other, but these are two that work. Part B asks for the D spacing. And you can find that using the A naught over the square root of h squared plus L squared plus K squared equation. And you plug in the HKL of the two planes that you found in part A. You end up getting 4.08 for the 010 plane. And the bar 102 plane ends up being 4.08 divided by the square root of 5. Which is about 1.82 in this case. Alright, so I'm going to go ahead and move this to the side so that we have a little bit more space to work with. Part C is going to ask us to sketch the reciprocal lattice for the 201 projection. And we're going to label the first 8. I want to do a couple more planes just so we can get practice of labeling planes, but you don't have to do as many as I do. Alright, so first we find H to use as our scale. H is the inverse of D, as in the reciprocal of D, or the reciprocal lattice, and that ends up being 1 over 4.08. You can use either plane, I just happen to use the 010 plane. Now you're going to set that value, the 0.245, equal to a centimeter, a half centimeter, 2 centimeters, whatever you want your scale to be. Right after that, you want to go ahead and draw a random origin, wherever on the page. And then 1 centimeter away, or whatever your scale was, you want to set that as your 010 plane, or whichever plane you chose to set as your scale. Now using that scale, we're going to go ahead and figure out how far away the bar 102 plane is. Once again, we're going to take the reciprocal of D, so 1 over 1.824, to be able to figure out, all right, well, we have 0.548 angstroms inverse. How many centimeters is that going to be? So we're going to set up a ratio with x being to 0.548 as 1 is to 0.245. We're trying to find the number of centimeters that x is, which in this case is 2.238 centimeters away from the origin. The angle between the 010 and the bar 102 is 90 degrees, so we can just draw that as a rectangle. Notice how it's about 2.238 centimeters away. So I'm going to go ahead and now draw the rest of the lattice using the points that we just drew. Once again, I'm doing way more than is necessary, but it's just for practice. The way you find these planes is if you're moving up and to the right, you add bar 102 and 010. But if you're moving up to the left, you subtract the 010. If you're moving down, you subtract the bar 102. And if it's all based on directions and paths from the origin. So if you're 2 away to the right, then you're at the 020. And if you're 2 away to the left, you're at the 0 bar 20. Same thing with the up and down directions. You just use this, the planes that you defined in the very beginning. Alright, so after we've drawn that, which once again is way more than we need to, I'm just going to scale it back down to the actual number of planes that we need. Once we have that, we want to go ahead and confirm that this is an FCC using the structure factor. The structure factor equation is, once again, little f e to the 2 pi I HU plus KV plus LW. We know since it's an FCC, it's going to have 4 atoms in the unit cell, or 4 terms in the calculation. And these atoms are going to be half on the faces and 1 in the corner. Notice this is 4 terms in the unit cell, but there's still only one basis, the gold. The points where these atoms actually are at the 0, 0, 0, 1 half, 1 half, 0, 1 half, O, 1 half, and O, 1 half, 1 half. Just different combinations of 0 and 1 half, 1 half. And these are going to be your UVWs that you plug into your structure factor equation. So I'm going to go ahead and actually write the simplified version of the structure factor equation. You can go ahead and double check this by actually plugging in each individual point, but I'm just going to skip that part just in case this video ends up being too long. So once you've figured out the structure factor equation, you want to go ahead and pick the FCC planes that you know are going to diffract, and that's going to be the 111 and the 200, because the 111 is either all odd and the 200 is all even. So we know they're going to diffract an FCC. So we want to go ahead and make sure that the structure factor doesn't equal 0 for those two planes. And keep in mind, if e to the pi I is multiplied by an odd number, it's a negative one, and if it's an even, it's a positive one. And that's where these numbers are coming from. And it's going to be e to the pi I with negative 2 plus 1, so it's a minus 1, and then we're going to have another minus 1 at the end. So they both equal 0, so neither of those planes that we pick diffract, or any of the two random planes in your lattice. So none of the planes in the drawn lattice actually diffract, but that doesn't mean that no planes diffract. Alright, this is question 6 of the final exam review, and this is going to test your ability to index diffraction rings depending on A naughts and camera constants. Alright, so they've given us a wavelength and a camera distance, and from that we can find our camera constant. They've also given us the lattice constant for gamma FCC iron and BCC iron. So the camera constant is going to be the wavelength times the distance, which in this case is going to be about 5.02 angstrom centimeters. This is important when we're trying to figure out the relationship between the d-spacing and the radius of our diffraction rings. So we can go ahead and solve for the radius of the diffraction rings that we're eventually going to draw using the d and the camera constant. It's going to be about 0.199 times the d-spacing. Alright, so we're going to go ahead and write all of the planes that we usually test for diffraction down and figure out which ones would diffract in BCC and FCC. Keep in mind, BCC has to add up, all the indexes have to add up to an even number, and for FCC, all the indices have to either be all odd or all even. So we're going to label the BCCs as blue and the FCCs as orange, just for clarity. So these planes diffract for FCC, and these are the ones that diffract for BCC. Some of them diffract for both. Alright, now that we have our planes, you can use less planes. I just used multiple to make a point. So for BCC, the planes that are diffract are going to be the following, and their corresponding d-spacing we're going to find using our A naught over the square root of h squared plus k squared plus l squared equation. So from that, we figure out the A naught for BCC is 2.87 angstroms, and 2.87 divided by root 2 for the 110 plane, 2 for the 200 plane, root 6 for the 211, and root 8 for the 220. We can do all that math. I'm just going to do 2 planes per BCC and FCC. I think that's more than enough. So we figure out, okay, the d-spacing for 110 is going to be 2.03 angstroms. For the 200, it's going to be about 1.435 angstroms using that math. We're going to do the same thing for the FCC's first 2 diffracting planes, and that d-spacing is going to be the A constant for FCC, 3.65 divided by root 3 for 111, and 2 for 200. It's going to be 2.107 angstroms for FCC 111, and 1.825 angstroms for FCC 200 plane. Now that we have our d-spacing, we can actually figure out the radius of our rings based off of that relationship we had originally derived using the camera constant. We're going to multiply all of the d-spacing by 0.199 to figure out the radius of the rings that we're actually going to draw on our paper. So you're going to go ahead and multiply all of those d-spacings by the 0.199, which is just 1 over 5.02, the camera constant. And now we have all of the radii for each ring of the diffraction pattern. I'm going to go ahead and say 2 boxes is about 1/2 centimeter, and go ahead and label these with colors so that it's easier to see. So now I'm going to go ahead and measure 0.404 centimeters from the center, 0.286 centimeters from the center in 4 different directions, 0.419 centimeters from the center, and finally 0.363 centimeters from the center in green, and all of their corresponding colors. And I'm going to go ahead and draw the rings. On an exam, you're not going to have all of these different colors, probably just a black pen or blue pen, whatever. Just, you can go ahead and actually physically label them, but in this case, since I have colors, I didn't want to go ahead and label everything. Alright, and that's it.